Okay, so for topic three, we're kind of going to look at the speed of light and how we actually have come up with a value for it. Okay, so remember, Maxwell had kind of worked out a speed, and it was based on the constants that governed electricity and magnetism. And since light is an electromagnetic wave, it makes sense that it would kind of be governed by the same constants. Okay, now, truthfully, I'm kind of putting the egg before the chicken or chicken before the egg there, whatever, right? Because remember, Maxwell was just trying to unify electricity and magnetism. It's just that when his equations gave the speed at which these electromagnetic waves could propagate at, and it so closely matched the experimentally determined speeds of light that had been found, that's when he put together that maybe light is one of these electromagnetic waves that I've been studying and mathematically analyzed. But again, science, we should observe it, right? We should try and see if we can actually experimentally see this speed of light in action. So other scientists had tried to, some before Maxwell, others after. In fact, so because it was so, as we know, the speed of light is fast, right? At least for us in our everyday experiences, that's a very high speed, 300,000 kilometers every second, okay? Measuring it would require big distances and small times, right? If you're going to get a good read on V, and V is d over t, well, if V is really big, you're going to need to look at a big D and a small t, okay? So the big distances, that part's easy. It's the extremely small times. That's going to be hard, right? Big distance, sure. Go far apart to do your experiment. But the time, getting a time that accurate, that would prove difficult. And that's kind of essentially what these four experiments boil down to, is getting a better and better grip on how to get that precise time that's required, okay? So these are kind of, there's more scientists obviously involved. These are the ones kind of famous in the Western science, first of all, and realistically, these are the ones that often come up on the diploma. Okay, so you do kind of need to know these. You need to know the order, and you need to generally know what each scientist did. So, like a common diploma question might be like a two-parter where it would say, okay, which scientist did this, and do a calculation to calculate their speed of light. Okay, so these are in order. These are in order from earliest to most recent, out of these four anyway. Okay, this one has been fine-tuned ever since. All right, but we basically start with Galileo using lanterns and mountaintops, Romer using the moon of Jupiter, Fizeau using his rotating toothed wheel. Maxwell comes out between Fizeau and Michelson. Okay, Michelson, then his experiment really confirmed what Maxwell had predicted, and then it looked really, really good. Okay, so we'll just go through these four today, kind of the basics of what they did and how well it worked. So first up, Galileo. In 1638, he did this experiment, okay, and he was measuring a speed, so he used V equals d over t. They're all going to use that, okay, where the distance was the distance between two mountains. How did he get the time? He used his pulse, and he used visual cues just to see, okay, light's there, light's gone back. So he just said, have I seen what I need to see? And using his pulse to measure, because remember, there were no clocks back then, right? Galileo, pretty incredible. He didn't even have a clock, right? In fact, most of his work that he did on gravity and stuff like that and the motion of objects, he had to use either his pulse or he came up with a clever way to do it on ramps. No clocks, right? So he used his own pulse to measure the time that light took to travel from one mountain and back. So here's the basic setup. Galileo stood here. He actually stood next to the assistant, right? But he had the assistant. He said, okay, open the shutter on your lamp, right? On your lamp, open the shutter. And then this guy way over here was another one of his assistants, and he told that guy, okay, when you see our light, you lift the shutter on your lamp. And then when I see the light from your lamp, I will know that light has gone from us to you and back again. And then there we go. I know how far this is, right? The distance, of course, would be 2 times the distance between the mountains because it has to go there and back. So we got D, and then I'm going to measure T with my pulse. However, no matter what, no matter the distance, no matter how far apart these mountains were, he found that it was always taking the same amount of time. The time was always the same no matter the distance because it was just his reaction time, right? Light had gone there and back way faster than he was actually even able to even react to it, let alone accurately measure it, okay? So kind of a failed experiment, right? But you got to give the guy credit. It's the 1600s. He's trying to measure the speed of light without a clock even, right? So what was he able to conclude? I mean, all he could really take out of that is light's fast, right? It's very fast. Maybe it's instantaneous because this wasn't ruled out yet. Maybe light is instantaneous. Maybe when light leaves something, it just hits you, right? No time actually passes. It's just there. This experiment doesn't rule that out. They weren't sure that that wasn't the case. Okay, so Galileo, 2 mountains, 2 lanterns, tries to figure out how long it took to go back and forth. Okay, so just to work out what Galileo was working with here, okay, the average time it takes a human to react to any visual stimulus is 0.25 seconds. Okay, so that's how long it takes the average human to even realize that they need to react to something. So for their brain to even register that, hey, something's going on. Okay, so compare this to the time it would take light to travel back and forth between the two observers in the diagram if they are 2 kilometers apart. So remember, it has to go back and forth. So it has to go 2 kilometers that way and then 2 kilometers back again. So D equals 4 kilometers in total, right? That's how far the light actually went. So use D equals D over T, right? That's how you find the speed of something, okay? And realistically, Galileo probably didn't even reach the point where he was plugging in numbers because he saw all of his times being the same and went ahead and said, yeah, this is probably just how fast I can react. But let's just see, right? Let's compare the time, the time light would have actually taken. Now that we know the V, let's see how long that would have taken it and compare it to a human reaction time. So T equals D over V equals, well, D we just said was 4 kilometers. And the speed of light we know is 3.00 times 10 to the 8th power meters per second. Very fast. So how long would that actually take? I got 1.3 times 10 to the negative 5 seconds, right? So we're comparing 0.25 seconds, the human reaction time, to 0.000013 seconds, right? So that is obviously way bigger. So Galileo did not have a chance of doing it this way, right? We were going to need a much more accurate way to measure the time. So then Romer came in. Now, Romer's big advantage here was not necessarily that he was measuring the time super accurately, but the time was bigger. So the margin for error was a little bit smaller. He found a way to make the time it took for light to travel to get longer, and by making the distance really big. Okay, so Romer was actually an astronomer. So Romer was purely kind of an astronomer. He wasn't that interested, honestly, in the speed of light. However, his data would become crucial for looking at this calculation. So Romer basically studied the period of Jupiter's moon Io. Remember, period, what does that mean? Period is time taken to complete one full orbit, essentially, right? So he very well knew how long it took Io to go around Jupiter and then come back around and end up in the same place it started. Okay, now if it's going around Jupiter, you're going to see it disappear behind Jupiter for a while. What's called eclipsing, right? It was getting eclipsed by Jupiter. So it was very well known, it had been studied extensively. You can see this moon with basically a child's telescope, actually. So this had been studied for a long time. Shout out to Galileo from the last experiment. Io is one of the Galilean moons because he was the first one to observe them. Okay, the 4 moons of Jupiter that you can see with a pretty basic telescope. Anyway, Romer noticed that Io would come out from behind Jupiter earlier than scheduled, okay, when Earth was closer to Jupiter. And it would be a little bit later than scheduled when Earth was farther from Jupiter. So Io had a very clear rotational period. He knew very well that it took about 42 hours to go all the way around Jupiter, okay? However, when he did the math, he said, okay, 42 hours, 42 hours, 42 hours, so I should be seeing it now. It was a little early. It was a little ahead of time when he was there. The 42 hours didn't quite work out perfectly. It came ahead a bit earlier when he was really close to Jupiter. And when it was really far away from Jupiter, it was a little delayed. He's actually seeing it now, and he waited, and then it appeared. Okay, so it wasn't just going exactly 42 hours. As Earth was getting a little bit closer, it was popping out a little bit earlier every day. And as Earth was getting farther away, it was popping out a little bit later every day. And Romer actually cleverly put together that this isn't actually Io's orbit changing, right? As we know, gravitational orbits are pretty well defined. Earth is pretty stuck at 365.25 days to go around the sun. That really doesn't change much. And so it would be weird if Io's orbit was changing this much, because he was noticing about plus minus 22 minutes. So between the biggest delay and the biggest early time, there was about 22 minutes of gap. which is pretty big when you're talking about something like this, right? If Earth was off by 22 minutes every day, pretty quick, things get messed up. Okay. So it was just the fact that he realized it's just the fact that light from Io was taking shorter or longer amounts of time to reach Earth because of the differences in distance. So here's kind of a diagram of his setup, right? So we can kind of see that. Look at that. When Io appeared behind Jupiter and we were really close, it only had to go that far, right? It only had to go that far. So we'd call that maybe D close, right? However, when Io appeared behind Jupiter and we were way over here, it had to go way farther. And so we could figure out, well, okay, if we take the difference in time, well, that's just telling us how long it took light to cover that extra distance, right? So how about we call that D extra, which is just D far minus D close, right? That's the extra distance it has to travel when Earth is far away from Jupiter, okay? Now, did Romer actually do this? Not really, because he wasn't that worried about the speed of light. He probably would have liked to know, but it wasn't his goal. However, Huygens, the wave guy, you might remember, right? He was very interested in the speed of light. So he said, hey, Romer, can I use all your data on this? You've kept good track of the time. You've looked at the distances. Can I take your data and see if I can figure out the speed of light? And Romer said, sure, knock yourself out. So Huygens took his data, used V equals D over T, where D is this extra distance, right? So D is just this extra distance that it had to travel, which, if you look at it, what is that extra distance? Well, that is just the diameter of the Earth's orbit, right? That's just, if the Earth's orbit is a circle, not if the Earth's orbit is a circle, right? So that's just the diameter of Earth's orbit, which equals the D extra. Should make it actually look equal. Okay, so he just took that D. T was the time delay Romer had worked out. So T was the difference between time. So in other words, usually it would get to us now, but we're over here. So it's taking light this long to travel. And that difference again was about 22 minutes as Romer had worked out. So T was the time delay. D was the diameter of Earth's orbit around the sun. And using V equals D over T, what did Huygens come up with? He came up with the fact that light travels at 2.3 times 10 to the power of 8 meters per second. Hey, not too shabby, right? We know now it's about 2.998 times 10 to the 8 meters per second, okay? Not bad. Considering especially that the Earth's orbital diameter was not known as accurately as we thought at the time, right? We were pretty confident with our value of the Earth's orbital diameter. Turns out we were a little bit off back in this time. So yeah, the math, there was nothing wrong with the concept really. It was just that we kind of were using the wrong numbers. Okay, so not bad, 23% difference. We're talking about a very fast speed here. And again, let me remind you, it's the 1600s, right? 1676. So give them a break. All right. Now, Fizeau, this is the first time we would get really, really quite close. Okay. So light would basically pass through. He had this apparatus that you kind of see here, right? So he would send light. He would use lenses and all that. That's not actually super important to just understanding how the setup worked. But he would use light, send it through the gap in a toothed wheel. So in other words, if you're looking at this thing here, you're trying to send light through here, right? If you get light to send through there, then, okay, now it's on its way to a very far away mirror, okay? It's on its way to a very far mirror, and it's going to come back. Now, if it hits a gap, okay, you're going to see the light. Chances are, with how fast light goes, it's probably going to just hit the same gap, right? Light goes really, really, really fast. However, if you can get a wheel that spins fast enough, you might be able to get it to the point where, and I'm just going to draw the outline of what it would look like, where this goes exactly one gap's length over to the right. So that where there was a gap before, now there's a tooth. Okay, so that red equals the position of wheel when light returns. Okay, if you can get it so that it has just everything, it has moved one gap or one tooth, they're the same width, so it doesn't matter. If you have moved one of them over, then the light will be perfectly blocked. And it doesn't matter when light gets through, because then the next gap will be there. So what you do is you start spinning this faster and faster and faster and faster. What you'll see at first is, yeah, you'll see the light, no problem. It's going to go there, come back through a tooth. But if you can find the exact frequency at which it perfectly blocks it, okay, well then now every time light gets through a gap, it comes back and it hits a tooth. So to go back to kind of the notes here just quickly, so light passed through one gap, continued to a distant mirror. So light passed through a gap, continued to a distant mirror, reflected back to the wheel again. The wheel speed was adjusted so that you found where the next tooth, not gap, was now present when the light returned. This would block the light on its return trip. And so what you would see was just darkness. Every time light was getting through, it was coming back and hitting a tooth. Okay, so now here's the thing. You're spinning the wheel, right? You have it hooked up to gears, which spin at a very precise frequency, essentially. So you know that. Well, that means you know its period, right? Because period is just 1 over the frequency. So if you know how many spins it's making in a second, well, then you know how long it takes to make one spin. Since these are evenly distributed, the teeth and the gaps, well, then the amount of time it takes for one tooth to get to where one gap was, well, that's just 1/nth of a rotation, where n is the number of wheels or number of teeth and gaps, right? So essentially, to go there, right, it's taken not a full rotation, but since these are evenly spaced, then just whatever fraction of a full rotation that is. So what it's saying is the time it took for a tooth to be in the place where a gap just was will just be the total period of the wheel's rotation divided by the number of teeth and gaps. So for example, if there were 16 teeth and 16 gaps, well, then that means there's 32 kind of even splits around. And so if a tooth has just come to where a gap was, it's just made 1/32nd of a full rotation, right? It's taken 1/32nd of a full rotation. I'm not going to draw one like that, but you could picture it. What if we had 4 teeth and 4 gaps? Okay, pretending those are about evenly equal, right? So that essentially we have 8 things, 8 teeth and 8 gaps that are all the same size. So 1, 2, 3, 4, 5, 6, 7, 8, right? Well, how long does it take? How much of a full rotation does it take for 1 to get where 2 is? Well, 1/8 of a rotation, right? So if you know your period divided by the number of teeth and gaps, you've got the amount of time that's taking. Hey, okay, think about this. That's how long it took. If you're perfectly blocking the light, that fraction of your full period is just how long it took light to travel to the distant mirror and back. So what have we got? We've got a D and a T. Do you feel that? Don't you feel the shivers of excitement? We're about to figure out the speed of light pretty accurately. We've got a distance. We just worked out how long it took to perfectly block that light, right? So when Fizeau did this calculation, okay, when he did it, he figured out that light travels at 3.15 times 10 to the 8 meter per second. Okay, my gosh, 5% difference. 5% difference compared to currently accepted values. Okay, so this is a much more accurate result, absolutely. And what did Fizeau want to do? He wanted to say, okay, well, I can make this better. If I make more teeth and more gaps, well, then I get a more precise time, right? Because then it has to be even more perfect to block the light. So he tried to do it, he tried to do it, he tried to make them even smaller and smaller and smaller and smaller. Realistically, he was doing it very small already, okay? I think he had 720 slits. So he tried to do it, but he ended up finding out that light's wave properties get in the way. Light, when it passes through a very small slit, for reasons we'll get to later, it diffracts, okay? So it starts to get messed with a little bit. It starts to interfere with itself is what it's doing, okay, as a wave. And so there was kind of an upper limit on how accurate this could get. So smaller spaces led to wave diffraction, putting a fundamental limit on the accuracy that could be achieved using this apparatus. Okay, so he could have made it better if light wasn't a wave and it didn't diffract. Okay, Michelson said, okay, I like what Fizeau did. Now, this is after Maxwell, keep in mind. So Maxwell's gone and made his predictions on the speed of light, and the world is looking pretty fondly at them. Now, Michelson is going to come along and say, I like what Fizeau did, but he ran into the problem of diffraction because the light had to pass through a gap. So light diffracts when it passes through a gap. We'll do that in super depth later, okay? But he said, how could I make a similar setup where light doesn't diffract, where it's not passing through a gap. I said, well, I could kind of get the same idea going if I used mirrors instead of a gap that the light has to pass through. Because when light reflects, it doesn't diffract or refract or anything like that. It just reflects and keeps on going like it was before. Okay, so Michelson took Fizeau's idea and improved upon it by replacing the teeth and their diffraction problem with an 8-sided rotating set of mirrors. Now, this got even more accurate because to get it right, the amount of rotation needs to be almost exact. If it's off even a little bit, it's going to shoot the light away in the wrong direction and you won't observe it. So I'll just show you the setup here so you can kind of visualize, okay? But essentially, your eye is here at the telescope. So get used to drawing eyes a lot. They're going to be important in this unit. Okay, so here's your eye. And what you do is you shoot light. Okay, you take a light source, you bounce it off of this face here. Okay, so obviously your light source has to be a bit more direct than this, but oh well, you get the point. Okay, you shoot light here, you hit it at the right angle, it gets sent away to a mirror that's, again, just really far away. Okay, and then it comes back. Now, if it hits even at a slight angle, it's not going to work. Okay, but if you hit the point where this thing looks exactly like it does now, except everything has rotated 1/8, right? So in other words, this face is now going to be here, and this face is now going to be here, and this face is now going to be here, and on and on. You get it, right? Well, then you can end up with this. So you set it up so that when it's sitting still, it looks like this. Then you start to spin it. You won't be able to see anything. Spin it faster and spin it faster and spin it faster and spin it faster, and suddenly you're going to see light. Because what you've done is you've hit the point where exactly 1/8 of a rotation, right? If you're a little bit under, it's going to get bounced in the wrong direction. If you're a little bit over, it's going to get bounced in the wrong direction. But if you're at exactly 1/8, then you're going to be able to see the light source reflected to you in the mirror. And hey, you're going to have the time it took for the light to go there and back. Don't forget that, there and back. So let's try and be Michelson. This is one of those calculations that you do and you just feel almost a spiritual sense of peeking behind the curtain of the universe, kind of, right? You see, this is one of those fun footsteps to follow through. So we're going to do what Michelson really did. We're going to make that calculation, okay? So the mirror is spun at 533 rotations every second. So that's our frequency, rotations per second. Careful, not period. Rotations per second is the frequency. And the distance to the fixed mirror is 35 kilometers, okay? So be careful. How far did the light actually travel, though? It did that twice. It went there and back, right? Okay. So these really are the numbers from Michelson's experiment. Ooh, exciting. If light was observed through the telescope, so in other words, positive result, right? We found the right frequency. What is the experimental value for the speed of light? Okay, can you imagine being Michelson sitting down to do these calculations? He must have just been trembling. Okay, frequency equals 533 hertz. Just going to remind you that a hertz is the same thing as an inverse second, or 1/seconds. Okay, so that's how fast he was spinning it. Great. We know the distance it traveled, the distance the light traveled was 2 times 35 kilometers, again, because it went there and then it came back. So equals 70 kilometers, or if you're okay with it, I'm just going to say 70,000 meters. Okay. Now, great. We know the frequency. We know how fast it was spinning. What are we trying to get to? Because remember, we're trying to get to a V equals a D over a T. So how do we figure out what our T is here? So we know that every second it's spinning 533 times. Let's go ahead and work out what that means the period is. So the period would be 1 over the frequency, right? In other words, how many seconds for it to do one full rotation? Maybe you can see where we're going with this. How many seconds to do one full rotation? Well, that's 1 over 533 inverse seconds. So we have 1 over inverse seconds. That's just going to be seconds, right? So I got 0.001876172 seconds. So that's how long roughly it takes to do one full rotation. Did it do a full rotation? Not quite, right? It didn't do a full rotation. It did 1/8 of a rotation. So how long did it take light to go there and back? It took the same amount of time that it took this wheel to rotate 1/8 of a rotation. So our time then equals 1/8 of our period, right? Equals 1/8 of this guy. 0.001876172 seconds. I'm just going to go ahead and plug that right in. Okay, you can calculate it if you want, but I've got the time, so I'm just going to put it in. So V equals D, 70,000 meters, over T, which is 1/8 of 0.00187676172 seconds. And so, can you feel your heart beating? 70,000. Oh my gosh. I got 2.98 to 3 sig digs times 10 to the power of 8 meters per second. Do you know what the accepted today in 2020 value is for the speed of light? 2.998 times 10 to the 8 meters per second, right? He was very close, right? We're looking at about a 0.4% error in the early 1900s, right? 1905, okay? Wow, pretty cool. Now, you don't have to use an 8-sided mirror. You can use a 12-sided mirror, and in fact, they will throw those at you. They'll throw all kinds of sides of mirror at you. Do you need to memorize this equation? Not really, okay? I mean, if you want to, sure. It's not on your data sheet, your formula sheet, so you got to know it, I guess. But let's think about this, okay? It's asking us to, looking at this one, okay? The speed of light is equal to, for a FISA, I should say, not always, but for a Michelson apparatus. Otherwise, those numbers are kind of meaningless, right? But can you see why this is just V equals D over T? Well, what I said, right? Like if you can explain why this is just V equals D over T, you don't need to memorize this, right? Forget you ever saw it. So, but you do need to kind of work it, be able to construct it from the data given, right? Figure out why D is D and why T is T. So what's D? D is distance from multi-sided mirror, flat mirror, far away. N, what's that? That's the number of sides on the mirror. Okay, and what's T? Big T, remember that's the period. So how long it takes to make one full rotation. So let's just break this down. Why is this D over T? Well, that just is saying then why is 2D D and why is 1 over N T T? Well, 2D equals D because light goes there and back, right? Okay, that one was a little more straightforward. Why does 1 over N times T equal T? Why does 1 over N times the period equal the time? Well, 1 over N times T, right? Break it down a bit. T is time for a full rotation. And N is the number of sides. So if you are going to get the conditions where you see the light, well, then you've made 1/nth of a rotation. So for this, it was you needed to make 1/8 of a rotation, right? So what fraction of a rotation have you made times the time it would take, and there you go. That's the time. Fraction of a full rotation needed to work, okay? And so that's why that equals the time, because the time taken to complete 1/nth is when you will see the light source. Okay, so that's all we're saying there, right? D and T, yes, it's a little more complicated to get T, but not really, right? So you might already be thinking, hey, I could improve on Michelson's experiment. I could do a more sides on the mirror. I could do a dodecagonal mirror, right, with 12 sides. And then, hey, my timing would be a little more accurate. You're absolutely right. That's what they kind of went on and did. They fine-tuned from there, and it's been fine-tuned and fine-tuned and fine-tuned. As well as the math that Maxwell did was also fine-tuned, and we have both a theoretical and experimental more accurate value for the speed of light in a vacuum. Okay, and that actually wraps up 13.2, which is all about the speed of light. So if you're looking for practice, you can try that whole assignment. Again, what do you need to know? Just in general, the order of these 4 experiments, okay, the names, and roughly be able to understand what they did, be able to somewhat explain how they use their apparatus to measure the speed of light, or to fail in measuring the speed of light if you're a Galileo. As well as specifically for a Michelson type apparatus, okay, you do need to be able to be given the data from this type of experiment, be able to work out the experimental value for the speed of light. Okay, so if you're given the number of sides on the rotating mirror, you're given the period or the frequency at which you see the light source, and the distance between your rotating mirror and your fixed mirror that's very far away. Okay, so given those data values, you do need to be able to work out the experimental speed of light. There is lots of that in the 13.2 assignment if you're looking for practice for that. And when you feel all good about that and feel good about the other topics, that actually wraps it up for this week. So make sure you ask me any questions you got, come to Flex or just email or whatever. But when you're feeling good, you can go ahead and do the summative check-in for this week as well. Okay, see you next week.